I'll be right back.
When did you arrive?
Sorry?
When did you arrive?
Oh, I arrived ages ago because I was going to a friend's wedding. Yeah.
So, 2 days ago.
I've had like friends get married.
It's freezing, no?
No, it's okay.
Because you are going to be moving.
Yeah.
Can we change the temperature? It's freezing.
The answer is we can try.
You need to find a compact circle and change the radius.
Okay, very good. Pleasure to have Carlos telling us about your spinners.
Okay, so I'm going to talk about superstring perturbation theory, and I was asked to emphasize the role of the pure spinor formalism. So with pure spinors. And the motivation really is to compute as many amplitudes that you can, and ideally with many external particles and with many loops as possible to compute. And but why we want to do that? And that there are many reasons to compute scattering amplitudes in string theory. One of them is that once you compute the scattering amplitude, you learn more about the theory. You arrive at the result, and then you look at that result, and you can reverse engineer the effective action that gives rise to that amplitude that you computed. So you are able to determine the terms in the effective action, and you learn more about the theory once you do that. For example, the r to the fourth term that Juan was mentioning yesterday, you can. We know that this term is there in the effective action because we computed the 4-point amplitude and found this term. So in general, you can compute scattering amplitudes of gravitons, and you will find corrections to the Einstein-Hilbert action, and then you may do many things with the result. So you can, for example, check what are the implications to the entropy of black holes and things like that. So that is one motivation to compute amplitudes. We learn more about string theory in doing that. The other motivation is to get information about the field theory amplitudes as well, because you compute the scattering amplitudes of strings, and strings have a finite size. So you may ask yourself at the end of the calculation, what happens when you set the size of the string to 0? And so so you shrink the string to 0, the size of the string to 0, and it becomes a point. And the end result of doing that is that you find the amplitudes of point particle field theories. And two prominent examples of that are the n equals 4 and n equals 8 theories in 4 dimensions. You can compute amplitudes in those theories in principle by first computing the string amplitude and then taking this field theory limit, where basically you set alpha prime to 0 and then you compactify the extra dimensions. And so yeah, so that's another motivation. And for example, there has been a lot of discussions about whether n equals 8 supergravity in 4 dimensions is ultraviolet finite or not. Okay, no. And one way to try to answer this question is to actually compute the amplitude. To answer this question in field theory, nowadays the task is to compute the 5 loop amplitude for 4 points in this theory.
Can you write a little bigger?
Okay. Yeah, but okay, I was planning to erase these anyway, but
Then you don't need to write it at all.
okay, yeah. Yeah, that's a good point.
You should write it.
Okay. So one way to compute to decide about this question is to compute the 5 loop amplitude in this theory. But people are trying to do this, and it's very complicated. So another way that you can, in principle, determine the answer to this question is to compute also the something like this. So now you have the 5 loop amplitude in string theory, and that is the only diagram that you need to compute. It's yeah. So in principle, it should be simpler than computing the amplitude directly in field theory, because in this case you get many diagrams to compute. But so far no one has computed this amplitude. So it's a research problem.
Sorry, one question. So normally you get into say compactifying 11 dimensions of gravity, and here you 10 dimensions.
Oh.
Does that factor change more?
No, well, you compactify 6 dimensions. You go from 10 to 4 by compactifying 6. Okay, so there are many other motivations to compute amplitudes, but I would spend too much time talking about them. Okay, and I forgot to mention one motivation, and but let's okay. So we want to compute scattering amplitudes in string theory, but up to like 15 years ago, these calculations were very difficult to do. If you wanted to compute an amplitude, you would have a lot of trouble. And there are two. And why these amplitudes were difficult to compute? And people came up with two criteria to classify the sources of these difficulties. And one criterion is whether your formalism has space-time manifest ten-dimensional supersymmetry, and the other criterion is whether your formulation can be covariantly quantized. So whether there is a covariant quantization. And up to 15 years ago, the two mainstream formulations of the string theory were the RNS and the Green-Schwarz formulations. And in this case, manifest spacetime supersymmetry is a complicated business, but it can be covariantly quantized. And in the Green-Schwarz, it's the opposite. You can more or less understand why these criteria are relevant, because the more manifest symmetries you have in your theory, the better it is to do explicit calculations. But in the year 2000, Berkowitz found out the pure spinor formulation, where both these issues are not there. So the formulation has manifest spacetime supersymmetry, and it can be covariantly quantized. So you can suspect just from this table that it will be easier to compute amplitudes. And in fact, using the pure spinor formalism, the endpoint amplitude at tree level has been computed. The general solution for the endpoint amplitude, and also for the open string and closed string. Also the endpoint amplitude at one loop, but there is a caveat here, that it's the low energy limit of these amplitudes, and also the 4-point and 5-point amplitudes at two loops, and the 5-point amplitude is also in the low energy limit, and more recently the 4-point amplitude at 3 loops, but also in the low energy limit. So the quest of my lectures will be to present the calculation of all the endpoint amplitudes at tree level, and both for the string theory, and also for the low energy for the field theory. So in this case that I'm going to show, it will be the Super-Yang-Mills amplitudes in 10 dimensions by taking the alpha prime to zero limit, as I mentioned before. Okay, so that will be the motivation, and in doing this calculation, I will come back to these 2 points, because the calculation was possible only because of these manifest symmetries that are present in the formulation. So but before starting to talk about the formulation here, I need to set up some conventions, and string theory is defined in 10 dimensions, and so we have vectors with a Lorentz index that goes from 0 to 9, and we also have two types of spinors. One which is the vial, and the other which is called the anti-vial representations, and alpha goes from 1 to 16 in this case, and these two representations are inequivalent, and there is no covariant way to raise or lower the spinor indices in 10 dimensions, and because the conjugation matrix is off diagonal. So it matters the position where you write the spinor index. What? Bigger?
Yes.
Okay.
It's a very big room, and from the far end, things that look big
Okay, yeah.
quite small.
Okay, I'm sorry. Okay, so and in 10 dimensions we have the gamma matrices that are in principle 32 by 32, but in this representation we are going to use matrices that, well, the Pauli matrices that are the off diagonal components of the 32 by 32 matrix. So these guys here have are 16 by 16 matrices, and they satisfy the standard Clifford algebra. Like that. So in particular, you have and a gamma matrix with many indices here. It's M1 to Mn is the antisymmetrization of many like that, and another property that I will use all the time in doing the calculations is the symmetry properties of these gamma matrices, because as you can see there, we have the spinor indices, and so it's okay. So the gamma matrix with one index and the gamma matrix with 5. Okay, I'm
not sure. It's okay.
Right. Okay. Yes. So the gamma matrix with one index and the 5. So I will call them the 1 form and the 5 form are symmetric in the spinor indices, and similarly the 3 form is antisymmetric, and the 2 form has a different index structure. So the true form has one index that is downstairs and the other upstairs, and that is antisymmetric if you do this. And the 4 form is symmetric. And you don't need to consider as independent guys the gamma matrices with more than five indices, because because the gamma matrices with, say, more than 5 indices are related by the epsilon 10 tensor with the gamma matrix with less than 5 indices. So okay, and one last identity that is used all the time is this one. If you symmetrize alpha, beta, gamma in this combination and you contract this one, you get 0. And the proof for this one is on page 246 of the Green-Schwarz written book, volume 1. Okay, so these are the conventions that I'm going to use.
Just to make sure I understand, how many of these little gammas are there? There's 10?
Well, what do you mean? How many?
Look,
The
I just want to make sure I understand, because you can't find 10 gamma matrices that are 16 by 16 that all anti-commute. But these are different because you conjugated between the upper right and the lower left. Is that what you've done?
Well, you mean you doubt these?
I'm confused.
Confused.
There
Well, you can do this, and so if you want, for example, I can give you explicit matrices that do this job, and well, and
don't I need 32 by 32 matrices?
well,
10 of them?
you have them. If I give you the 16 by 16 matrices, you can construct.
Those 16 by 16 matrices are what you have in the upper left and the upper right and the lower left are the same or not? They're
No. They are not the same. One has downstairs indices and the other.
Okay.
Yeah, so they are the Pauli matrices in 10 dimensions. I don't know if that helps you, but it's. No. There is no covalent way to do that, and okay, we could talk about this in the discussion section, I guess, but okay, I was hoping that someone would say, okay, yeah, let's do that, but the way to construct something, so the idea to raise or lower indices is that you need to find an object that is invariant under Lorentz transformation, right? Just like in standard GR, that you have a quadratic invariant that it's like this, and then you identify these as the lower guy. Yeah, it doesn't make them dual because they are not Lorentz invariant just by doing that. You would need to contract. You would need to sandwich them with the charge conjugation matrix, and in 10 dimension this matrix here is off diagonal. So I think I'm so so it's off diagonal, and so if you decompose the spinor like this, so these are now the 32 by 30 the 32 Dirac spinor, and you want to check what happens if you consider, say for example, just this guy with the hope of defining what would be the psi with a lower index by looking at this expression here, because of the fact that this matrix is off diagonal, you get 0. Simply because you would pick you multiply 1 and then by 0. So there is no way to do that.
Do you mind writing down the charge conjugation matrix?
I don't know if I okay, it's 1 or minus 1, but that is the I think it's with minus with the convention that I use. I can give you my conventions for the gamma matrices if you want, but you need to check that this is really a conjugation matrix that satisfies things like it anti-commutes with gamma m and things like that. But let's move on. Where is the clock? Oh, I have one here, but okay. Okay, so I will now start to talk about the pure spinor formalism, and I want to motivate the introduction of pure spinors, and to do that we need to go to 1986 when Siegel proposed an action for that was meant to describe the superstring. So that's the action that he proposed, and these say sigma 1, sigma 2, and then you go from this to space-time. So these x and theta's there are maps from the two-dimensional surface to space-time. So okay, and so that was his action, and this action is well, you can compute the OPEs of these variables, and that's one, and then the other one is And this action is invariant under some transformations, and the transformations are del xm is transforms like this. Plus P alpha is a variable that is called the conjugate momentum to this guy. It's an independent variable. So the other transformation is del V P alpha plus V Z and del P alpha, and it's the same as so the action is invariant under these transformations, and these transformations are the conformal transformations for say and okay, so these defines CFT transformations, where P alpha is a variable with conformal weight 1, 0. Well, okay, and theta alpha has conformal weight 0, 0, and del xm has conformal weight 1, 0, and the bar simply swaps the 1 and 0. So the action is conformally invariant, and it's also supersymmetric, and so I'm telling you the good things about the action first. So it is supersymmetric under these transformations. Oh, by the way, when I write in parentheses, I'm contracting the spinor indices. So right. So okay, I will write this only once, and then that's what. These are the supersymmetry variations of the action, and they are generated. Oops. Okay, they are generated by the following charge. It's P alpha and then plus 1/2 and then plus 1/24 And you can check using those OPEs that this charge satisfies what is expected from a supersymmetry charge. Okay, so it's really supersymmetry. Okay, and you can do a bit more with the he had done a bit more with his approach. He defined new variables that are these ones. I'm writing these explicitly because I will use these all the time in the pure spinor formulation. So it's actually minus. So that is called the Green-Schwarz constraint. So Siegel was inspired by the Green-Schwarz formulation when he proposed that new approach for the superstring. So he wanted to have the same variables that were present in the Green-Schwarz. And
So in the superstruct written down there, the term number 24, is that theta, gamma, and t theta?
yes, yes, theta, gamma, m, del theta. Yeah, I'm sorry about my handwriting, but and
So when you say this is the Green-Schwarz constraint, you mean if you set this equal to 0 and then substitute that back in the action, you get the Green-Schwarz action?
no, it's not really like that, because you don't have d alpha there. You have p alpha, but
So in what sense is it a constraint?
so in what sense this is a constraint is you need to look at the Green-Schwarz action. It's well, you would have something like this, and then something like that, and plus the with the bars, and you also have a term like that looks schematically like this. And so in the Green-Schwarz action, you can ask yourself, what is the conjugate momentum to the theta variable? And so you want to quantize the action, say, and then you define the conjugate momentum to theta, and you compute it as usual. You would do something like that, and then what you will find is this part here in this computation in the Green-Schwarz. So if you now subtract one from the other, you should get 0, right? And that's the constraint. And but okay, and in the Green-Schwarz action, well, let me skip the quantization of the Green-Schwarz action, because well, actually let me say something about this. And so okay, so in the Green-Schwarz action, d alpha is a constraint in the sense that I mentioned. And so you want to quantize the theory by imposing that the constraint in your states are 0. But you would find that this leads to problems because I'm jumping a bit, but since you asked it, I think it's but
Well, it makes more sense later in your discussion.
okay, yeah. Because well, the green Schwarz cannot be covalently quantized. So what I'm going to do here, it's there is no solution. But I just wanted to mention the problem. But yeah. So but this problem will not be present in the pure spinner. So rest assured that things will be fine.
You also have a supercharge with an upper index?
No. Well, yes. You can. And so in the type 2, so one thing that I didn't do here was to write down the guide. So I'm restricting myself to the holomorphic sector of the theory. So but I'm writing down the variables that are left moving, but there are right moving variables if you want to describe closed strings. So you would have something that people usually write like with hats. So where for the type 2A theory, the chirality of the alpha variable is opposite to what you had before, and the type 2B, they are the same. And so you can get for the closed string, you will also have something that has a charge for the right movers, and this charge can be with lower or upper indices, depending whether it's type 2A or type 2B. So another definition is this capital pi. It's the supersymmetric momentum. And you can show using those OPEs that these definitions here are they anti-commute with the supersymmetry charge. So they are good once you want to have variables that are manifestly supersymmetric. So these variables are good for supersymmetry. And okay, so you have those variables there, and you can compute now the OPEs of these of these variables. And so you compute the OPE of the green Schwarz constraint, and you will get this result. That's one. And you get it's just a single pole. And okay, these are the two most important ones, but And you can also, these are really important for what I'm going to talk later. But so now you can also compute the OPE of this constraint with an arbitrary superfield that is, well, it's a superfield, depends on x and thetas, and at position w. And you find that this is d alpha m, just a single pole, where this d alpha is the supersymmetric derivative in 10 dimensions. And I'm going to write the momentum here instead of the derivative, but that's a convention that I use where I set I to 1. So if you compute the OP with that one, and then you get the momentum described by the superfield M. It's just a single pole. Okay, so these guys here are very important, and I will use them later. So okay, so I said the good things about the formulation, but now I need to talk about the issues with this approach, and fixing that issue led to the pure spinor formulation. And so, okay, so what are the issues? The first issue is that the energy momentum tensor has central charge different than 0. And the other issue is a bit more subtle, but in the second lecture we will come back to explain more about this. But the Lorentz generators for the spinor variables, the p alpha and theta, it's this one. You can compute it using Nader's method, for example, and this generator has level +4, where level I mean the coefficient in the double pole of sigma with itself. And at this point, this remark here is cryptic, but we are going to see the solution for this issue here in my next lecture. And so let's forget about this one for the moment, and what? Okay, it's the momentum of a particle described by this superfield. I'm jumping a bit ahead of my talk here, but in the second lecture we will have superfields to describe the particles, say the gluons and gluinos, and these will be those superfields. So they have a momentum associated to them. Basically the superfields will be will be expanded with plane waves to carry the momentum. So okay. So Km. Okay, so let me just sketch the proof for the first issue, that the energy momentum tensor has central charge different than 0, and using this invariance here, where say V of C is a analytic function, so or holomorphic, and it doesn't depend on Z bar, for example. So the action is invariant under these transformations if you have this, but then you can use the nether method to find out what happens if you now change the V to depend on Z bar as well, and then the variation of the action with this modified parameter is not 0 anymore, but it will be proportional to del V, this guy here, and whatever you get here, you call this the energy momentum tensor. Okay, I don't know if that's too basic, or people are fine with this way to get the energy momentum tensor, right? Okay, so if you do that to find the energy momentum tensor, you will get that's the result that you get, and the central charge. Did David talk about this? And the central charge is defined as the term with a pole of order 4 in the OPE of the energy momentum tensor, and then you get and then you have more terms, but so and then I said that this energy momentum tensor has central charge different than 0, right? And to check this, you can okay, to check this, you can use these OPEs here to compute another OPE to obtain this pole of order 4. So let's do one case. Okay, is this clear, or should I do this, or everybody are happy with doing OPE computations? I don't know. Okay. Okay. Let's do this just for completeness. So Oh, no, let's not do this. Okay. Okay. But okay. Oh. Let me do this for this part. So for that part, you will get. Okay. Let's be schematic. The central charge for this part will be -2 times. You will get a Kronecker delta that contracts the spinor indices, and I said to you that the spinor index goes from 1 to 16, so that's -32, right? And the central charge for the x variables is +10. It's basically the dimension of your space-time. So the central charge here will be C is equal to -22. Okay. And okay, central charge different than 0 means an anomaly in the CFT, and you don't want to do that. You don't want to have that. So what you can do here is you modify the Siegel proposal by adding a pair, by adding this term here, where these lambda and these omega are bosonic variables. And okay, so what happens once you add this term? You would get a central charge. Did I mention that P and theta are fermionic? But okay, so they are fermionic, and these lambda and omega are bosonic. So if you do the computation, you will find that because of this difference of being bosonic or fermionic, the central charge that you would get naively for that term is +2 instead of -2 times this, and then that's +32, and that doesn't fix the problem. Does not fix the issue. So what can you do here? The solution was found by Berkowitz, and he noticed that if lambda alpha is a pure spinor, then it has 11 degrees of freedom instead of 16 here. So instead of this one, but now if lambda is a pure spinor, you would get +2 times 11, and that's +22, and that fixes the problem with the central charge. And to see this, that so I need to define what a pure spinor is, right? So a pure spinor by definition is a bosonic is a spinor that satisfies this constraint for any gamma matrix. If you contract like this, you get 0. That's the definition of a pure spinor. So these are constraints, and the constraints will remove degrees of freedom from lambda. So instead of 16, you will get 11. And to see this, it's convenient to decompose the variables from SO10 to U5. And a spinner of SO10 goes to where A, B, so A and B go from 1 to 5. They are variables of the U5 group, where this guy is antisymmetric. So this is a 1, this is a 10, and this is the 5 bar in this decomposition. And using this decomposition, it's very convenient to solve this constraint. And you will get you will get oh, good point. The conformal weight of lambda is 0, so it's 0, 0, and the conformal weight of this is 1, 0. It's the conjugate momentum to lambda. I don't really want to answer that question because I'm slightly lying here, but so that's why I put quotation marks there. But it's a subtle issue that I hope I could get away with until the end of this talk. But so let just wait 5 minutes and.
Sorry, just to make sure I have the conventions right. So so can you outline where the minus 22 come from? Presumably each of the x's contributes minus 1.
Oh, okay. So the central charge coming from this part is plus 10. Each x contributes 1.
Oh, okay.
And the central charge for this one is minus 32. Each pair of p and theta, they contribute minus 2, and there are 16 of them. So the plus 22 here is that, well, and these are fermionic, and these are bosonic variables. And if you do the calculation, you will find that the pair of this pair contributes plus 2 to the central charge.
Okay.
Can you understand this new spinner variable as some ghosts? Some
Well, they are called ghosts.
But they can also conjugate fixing or something?
That's a good question, and there has been 15 years of research trying to find the answer to this question, and I think that it's more or less been answered a few months ago by Berkowitz himself, but I'm not going to try to explain his twistor derivation of, but okay, so let me just write down why it's 11 instead of 16. So I said that a pure spinor is a variable that satisfies this, and once you decompose to U5 variables, and you will find that that to solve this constraint, you would get something like this. Let me just write. So the 5 can be written in terms of the 1 and the 10. components of the U5 variable. So the 5 can be written in terms of the 1 and 10. So you get the 11 degrees of freedom from the first. So you get the degrees of freedom come from this part only. The solution, yeah. So the solution gets rid of the 5. Yeah. Okay. Before addressing the lies, I will talk about the covariant quantization. But so how the formalism is quantized, and to do the quantization, Berkovits, in his original paper from 2000, it's HepTH. So it's 5. So he proposed to construct. He postulated the following BRST charge. So that is the BRST charge to quantize the theory. Right, but we should check that since he wanted to quantize the theory using BRST methods, you need to check whether Q squared is 0, right? Because and this computation can be done. So let's check. Q squared can be written as the anti-commutator of Q with Q, and then you can use the OPEs to evaluate this. It's you get essentially you get you need to pick the single pole of the BRST current. So and that is the only contribution. And I wrote before this OPE here, right? So now you can use that result here, and you will find that this result is, well, -1/2, but lambda gamma m lambda pi m, and this is 0 because of the pure spinor constraint. So we see the need for pure spinors once more by imposing that we want to have a well-defined BRST charge. So yeah. Five minutes? Let me let me just say a few words that will motivate the second lecture, and then I will stop. So, okay, so that is the pure spinor formalism. It's this action with these OPEs and the BRST charge. So, well, the BRST charge here is covariant. It's manifestly covariant in space-time, so that is good for the column that I just erased. And it's also supersymmetric, simply because it inherits these properties here from the Siegel approach. So we have both manifest spacetime supersymmetry and a good covariant quantization with this BRST charge. And the BRST charge is not really complicated, right? It's just a pure spinor multiplying the Green-Schwarz constraint. But in order to compute the amplitudes, we will also need vertex operators. And I will just write down the prescription for tree level. So we want to compute amplitudes at tree level, and I will write down some things here, and I will explain them better later on. But the amplitude will be computed by the following path integral. It's so for the open string. Let's do for the open string first. N minus 2, and then a path integral of v1 at 0, v n minus 1, 1. So tree level for the Superang Mills multiplet. Let's then Vn at infinity and V, and then U2 at Z2 to Un minus 2 . So that is the correlation that we will need to compute. But I wrote this because I wanted to motivate, well, the introduction of vertex operators, and we want these guys here to describe the multiplet of Superang Mills, and but we want this prescription to be conformally invariant, and furthermore we want it to be BRST invariant because we are going to quantize the theory using BRST methods. So we want it to be conformally invariant. So the way to do this is to have this vertex V to have conformal weight 0, 0, and the U vertex will have conformal weight 1, 1. That will make it conformally invariant, and just you can understand this if for example, by definition, conformal weight H bar field transforms, well, let me just try. So this is invariant under So this guy here is invariant under CFT transformations. So these guys are being integrated, so they need to be, so there is one there. Well, actually just one because I'm doing open strings, but so that requires the conformal weight to be 1. And since there are no integrations associated to the V vertices, age must be 0, such that the whole thing is BRST, is conformally invariant. And BRST invariance will be satisfied by requiring the V vertex to be BRST closed, and the U vertex should satisfy this equation. It's the derivative of the V vertex, and these actually come from these are the same conditions as bosonic string theory. But there you have okay. So in the next lecture, I'm going to write down the solution for these conditions, and we will have the vertex operators to start doing calculations for the amplitudes. Okay, 5 minutes over time, right? Oh, you. Do I have like 5 minutes to try to make up the quotation marks there because I said that this is the arguments that I gave here were a bit hand wavy. I lied a bit about the computation of the central charge for these guys, but that is a let me just I will try to I will just sketch if I'm allowed.
5 minutes.
Yeah, 5 minutes. If you look at Berkowitz's original paper, he didn't write that term there. He didn't lie at any point. But so what he did was he knew that he wanted to have pure spinors, and he knew that the pure spinor has 11 degrees of freedom with these two variables. So he proposed an action to describe those 11 degrees of freedom, and not the would-be 16. So the action that you will read in his papers is something like this. Where he wanted to describe the plus component of the pure spinor with the S variable, and the lambda AB would be this UAB that appears in this action. So this action here contains only the real, the truly degrees of freedom for the pure spinor, the 11 degrees of freedom. But it's in U5 variables, right? It's related to the U5 variables. It's not really covariant in space-time. There is no SO10 covariance here. But anyway, he said, well, suppose that so from the action you can compute the OPEs of these guys, and it's the logarithm of Z minus W, and the OPE of V with U, they are the conjugate momentum to each other, so you get something like this: Kronecker delta anti-symmetrized AB CD with a single pole, and then he so these are SO10 variables, you in terms of U5 variables, but he wanted to have a prescription that is SO10 covariant. So what he did was he constructed now I think I'm this is more or less going to the direction that you wanted to hear, right? That no, it's no. I'm just writing an action for the 11 degrees of freedom for the pre-spinner, but now I need to couple that with that part of the action in a SO10 covariant way. So in what? Yes. So the quotes really should be this one. So this term here. And okay, so the way he did that was, well, the pure spinner is a spinner, so there will be a Lorentz current associated to the pure spinner, and it will be something like this, and this is really true. It's not, but the wow. So the way he did this is, yeah, well, well, yeah, okay, yeah. I think it's because I noticed that I needed to introduce other things, and I would need to decompose this guy into U5 variables and then propose a solution for these U5 for the decomposition of these guys in terms of S and U, and then check that everything works there, and then uplift the solution to SO10. But
12 seconds left. It's probably not enough. Let's do it next time. Let's thank God. So let's meet at 45. We have 20 minutes.
Can we drive that action by starting from that long action and solving the pure spinner constraint? So can we drive this action by starting from that and solving that? More or less you can do that. You can. I think you can derive these from starting from that action and then decomposing the spinners in this language, and then you will find that one. But you need to impose the gauge that WR is 0. that is the conjugate momentum to lambda a.
Oh, yeah.
Lambda a that was the guy that is not the degree of freedom, but I think he's
Thank you. Good. How's that? All right. So if we insert a single operator, we get some state on the sphere. So it's natural to ask what happens if we insert two operators. We just argued, so we have one operator at the origin and one operator at x. This gives some state on the sphere. We just argued that all states in the theory are linear combinations of primaries and descendants. And so this thing has some expansion as a sum over primaries in the theory and their descendants. And let me group together primaries and descendants into a single differential operator acting on a primary. Okay, so this is just a fancy way of writing OK of 0, p times OK of 0, p squared times OK of 0, and so on. So this differential operator will have some expansion in derivatives, and each derivative gives us a momentum generator. So this is an equality between states, but because of the state operator correspondence, when we insert this anywhere in a path integral, we get some equality between operators. So we'll often just write this as an operator equation. And we should understand that when we insert this equation into a path integral, it's true as long as all the other operators in the theory are outside a sphere surrounding x1 and x2. Okay, that's because it really comes from this equality between states, and this equality between states doesn't work anymore if there are other operators sitting around inside closer to the origin than x. Okay, so this is valid if other operators have x minus x1 bigger than x12. But there's something more general we can do. So we can imagine putting the operators at x1 and x2 and expanding in states at the origin. And this gives an alternative form of the OPE. So now we have some different differential operator that depends on both x1 and x2. Okay, of y equals 0. This first one is more convenient for us for doing calculations, but it's important to keep in mind that this second one is also valid. In fact, this one has a somewhat larger regime of validity. We can use this kind of OPE whenever it's possible to draw any sphere that separates x1 and x2 from the other points in the problem. So as an example, suppose we had x1, x2, x3, and x4. You might think it looks hopeless to do the OPE, but actually we still can, because we can draw a very, very, very big sphere like that with center down here and do the OPE between x3 and x4 and put them here, and x1 and x2 and put them at the inverted image of that point.
So does that converge very slowly or something like that?
Yeah, it does. I'll say a little bit about the rate of convergence at some point, but it always converges exponentially. It's just a question of what is the it converges exponentially in the dimension of the operators appearing here. So it's always r to the delta O, where r is less than 1. But the rate depends on what r is, and I'll define r later. Okay. Good. So we'll mostly use this form of the OPE just because it's easier for computations. It has fewer variables. This thing is a differential operator. And by dimensional analysis, it has the following form. So it's proportional to x to the delta k minus delta I minus delta j times some power series, 1 plus x times delta plus x delta delta, where I'm being unclear about the coefficients and the way the indices are contracted. And so this is just dimensional analysis, but more formally, exercise, you can show this by acting with the dilatation operator, and in this case, it's easiest to use the exponentiated dilatation operator, acting with this thing on this equation. So quick exercise, just act with that. You'll get some consistency condition on this, and that will imply that that dimensional analysis works. Thank you. Yes, plus ... Okay, and actually, I should have said something even more elementary. So the fact that the indices have to be contracted here is a consequence of rotation symmetry. And you could obtain that fact by also acting with rotation generators on this equation. But usually we just we don't think too hard about that. But the point is that so by acting with conformal generators, we can constrain C. And it turns out that acting with K mu, fixes C up to a constant coefficient. So this computation is a little bit more involved. We act with K on both sides of this equation. K is some differential operator that we know. So we get some derivatives with respect to x on that side, some derivatives with respect to y on this side, and some dimensions and spins and everything. And working order by order in the series expansion, you can fix all the coefficients in that expansion. So that's a little bit of an involved computation, and fortunately there's an easier way to see why the form of this thing is fixed by conformal symmetry, and also get some of the coefficients. And the idea is to take a correlator of our OPE equation with some other operator. So I'll take the correlator of both sides with OK of x3. And for this to make sense, let's assume that x3 is farther away from x2 than x1 is. Okay, so x23 is bigger than x12. Okay, so that's one side of the equation. And this is just equal to a sum over k prime, Cij k prime, x12 dx2, OK prime of x2, OK of x3. Okay, now this thing is fixed by conformal invariance, we already know, and we worked out its form in a previous lecture. It's given by some 3-point coefficient, Fijk, over a product of distances between points to different powers. Okay, x12 to the delta 1 plus delta 2 minus delta 3 times permutations. Okay, so the left-hand side is known. And the right-hand side, well, we have this, but this is also fixed by conformal symmetry. So actually, I should say here I'm specializing to scalars just for illustrative purposes. So the 2-point function of scalars we know. This is x23 to the 2 delta k And let's pick an orthonormal basis of operators so that two-point functions vanish unless the operators are the same. So this sum just collapses into a single term, Cijk x2 1 2 d2 x2 3 to the minus 2 delta k. And now so this thing naturally has the form of an expansion in small x12. So by Taylor expanding this thing in small x12, we can match all the terms. So as an exercise, you can try this in a simple case, and I'll show you what the answer looks like. So let's fix delta I and delta j to be equal to each other and delta phi, and I'll redefine delta k as just delta. So now show that Cijk is equal to Fijk, the OP coefficient, x to the delta minus 2 delta phi, 1 plus 1/2 x dot d plus alpha x mu x nu d mu d nu plus beta x squared d squared plus dot dot dot. And alpha is delta plus 2 over 8 delta plus 1. Beta is minus delta over 16 delta minus d over 2, d minus 2 over 2, delta plus 1, and so on. Okay, so the coefficients in these differential operators are just rational functions of the dimension that come from this this Taylor expansion and this expansion. Pardon? Yeah. Dot dot dot. So this is a differential operator. Yes. Good. So we're making a choice. So the two-point functions vanish unless operators have the same dimension and spin. So that is a consequence of conformal invariance. Now let's take all the operators with a fixed dimension and spin, and let's compute all their two-point functions. That gives a matrix. Now let's diagonalize that matrix and choose a basis of operators such that the matrix is diagonal. Okay, so that's a choice that we can always make. Thank you. That's right. We're also normalizing it. Yeah. So this is something that that you can always do, and that is conventional to do. Normalize all the two-point functions, and that's just the definition. You're defining the operators of the theory so that they have normalized two-point functions. Once you do that, the three-point functions become meaningful. That's new information that you can't normalize away. Yeah, it's 1/2. And we'll see why in a moment. Other questions? All right. So good. So just to be very explicit, you have these differential operators. You can work out what they are in principle by doing a lot of algebra, and they're just completely fixed by conformal invariance. So the only things that aren't fixed by conformal invariance are these OPE coefficients. So in general, well, we just saw a way to compute. If you like, you could read this equation the other way and say this gives a way to compute 3-point functions using 2-point functions and the OPE. So in general, the OPE gives an algorithm for computing any endpoint function of the theory. So this is an endpoint function. We pair up O1 and O2 and do the OPE, and this becomes a sum over K, C1 to K, X1 to D2, OK of X2 dot 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 On of Xn. And this is an n minus 1 point function. And by recursing, we eventually get down to 1-point functions. We could get to 2-point functions, which we know, but we can even get to 1-point functions. And these are very simple. So this is just 1 for the unit operator and 0 otherwise. And this is a consequence of conformal invariance, if you like. The 1-point function has to be translationally invariant, so it can't depend on the position. And then by dimensional analysis, it can only be non-zero for the unit operator. And actually, since we've been talking about thermal CFTs a little bit, this algorithm works on any conformally flat manifold. So you take some manifold, you do a Weyl transformation, so there's some region that's flat. And in that region, you can do the OPE, because you can just you can think of cutting the path integral so that you just have that region, and then the OPE is perfectly valid in there, and then you glue it in. And the thing that changes on a non-trivial manifold is this 1-point function condition. So on a non-trivial manifold, there can be some intrinsic length scale, and the 1-point function no longer has to vanish. So for example, on R d minus 1 cross S1 with radius beta, you can have O proportional to beta to the minus delta O, or temperature to the delta O. So this is in principle how you could calculate thermal correlation functions in a CFT if you knew the thermal 1-point functions. So now we can compute everything. But the algorithm that I gave you is not unique, because if I have some endpoint function, I could have evaluated it in a different way. I could have picked these two random operators and done the OPE between them and gotten some answer. And it would not be obvious that it was the same as the answer I got by doing this procedure. And we'll see this extremely explicitly in a moment. The condition that these two procedures give the same answer is associativity, which basically says that if you have O1, O2, O3, and you do the OP between 1 and 2, and then the OP, let me give myself some more room. You do the OP between 1 and 2, and then you do the OP between what's left and 3. This should give you the same answer as if you do the OPE in a different order. And if this is true, you can show that doing the OPE in any order in any endpoint function will give the same answer. Yes?
So we talked about how in principle we should only do the OP for the ones that are closer to each other in some sense.
Good.
But is there sort of a statement that we evaluated, we get some function of the x's, and then that, even if technically we had to assume that these two were closer and then this one is further out, the result we get doesn't care about that, so it then applies to all cases?
I would put it this way. There are configurations of points where the OPE is perfectly valid in different orders. Not
all configurations of things exist.
Yeah, there do exist some, and for example, this one, I can do the OPE in lots of different ways because it's possible to draw spheres that separate these pairs of points from each other. And I guess the only let's see, it should always be possible to do this. So there should be some way to also think about that OPE, and I'll have to think about that for a second. But anyway, at least these two are completely valid, and you can see you're not even close to violating the regime of convergence of these things. When you have configurations like that, then associativity is non-trivial.
It's a large endpoint function, or I have a point, and then it's surrounded by a ring of others, and then another one way over here, and then I wouldn't be able to do any possible order.
Yeah. Well, no, you would start doing them between the ones in the ring, and then eventually you would get to the point where you could do them.
So I was just sort of contrasting that with the statement that you could do this in any OPEs first.
Yeah, I mean, basically what will happen is the OPEs will sort of give you different Taylor expansions of the same function.
But they all converge to the same.
They all converge to the same function. So if you were strong enough to resum the Taylor expansion, then you would really see that every OPE is always equal to everything else. Yes?
It looks like if you have some configurations of points, it looks like
yeah. Yeah, you're right. That's the answer to what's going on here. So the OPE gives a sum, and part of that sum we can do. We can do the part of the sum that's determined by conformal symmetry, and we will find that when we do that part of the sum first, then we have better control over the convergence. So in particular, once we've done that part of the sum, we'll get something that manifestly transforms nicely under conformal transformations. And then we can do something like send this operator to infinity and then surround the other two with a sphere. And that might have been a little confusing, but hopefully I'll be able to make it more concrete in a second. Other questions? Okay, so the concrete example that we're going to love is a 4-point function. Of identical operators. So just for simplicity, let's consider identical scalars, phi. They have the following OPE. So it's a sum over operators. We have OPE coefficients times some known differential operators. Just to be very explicit, the operators appearing here can have spin. So let's give them some SOD index. And actually, so this was something that I forgot to mention a few lectures ago. So you can show that only even spins can appear in the phi OPE. And the way you show this is look back at the lecture for where I wrote the formula for a 3-point function of scalar spin L. And if you demand that those two scalars are equal, you'll find that the expression is just 0 when L is odd. Well, if you demand that the expression is invariant under permuting 5x1 and 5x2, then you'll see that it has to vanish when L is odd. Okay, so this is only over even spins, and by little a, I'm using a shorthand notation. It really means a collection of Lorentz indices. Okay, so good. So let's compute this using the OPE. I said you could. So this is equal to a double sum. There's one sum from this OPE, one sum from this OPE. So we have O and O prime, F phi phi O, F phi phi O prime, CA x12 d2, CB x34 d4 times a 2-point function OA of x2, O prime B of x4. Again, let's pick an orthonormal basis of operators so that this thing is just is 0 if O and O prime are not the same. And the 2-point function is fixed by conformal invariance. Okay, and this tensor we wrote a few lectures ago. This is equal to a product of these I mu nus.